Well, now the next topic is hydrophilic interaction chromatography, HILIC. HILIC. Okay? And this chromatography is not usual, okay? But it is very useful for small molecules, okay? Small molecules that are too polar to be retained by reversed phase columns, okay? Usually it's using reversed phase columns in the two polar molecules are not very well um, separated. So in the case, the stationary phase must be quite hydrophilic. Okay, so by the hydrophilic interactions with polar molecules, the separation can be good. Okay, so hydrophilic molecules are well separated, such as peptides. Yeah? Peptides are quite hydrophilic because it has amino and carboxyl groups and saccharides. Yeah, it has a lot of hydroxyl groups. Okay, so in this case also, uh, gradient elution is used. Okay, eluent strength is increased by increasing the fraction of water in the mobile phase. Okay, so mm, gradually increase the water fraction. Okay? Gradient elution goes from low aqueous content to high aqueous content. Okay, yeah, that's the idea. Okay? Here is the silica surface, and then now you attach this on. Uh, this is amino sulfonated this amine groups. Okay, this is quaternary ammonium salt. Yeah? So this has plus and positive and negative charges in the same molecule, uh, and it is called zwitterion. Okay, and zwitterionic bonded phase is used. Okay, and then the stationary phase becomes quite hydrophilic, or on the bare silica, you attach these silanol groups. Okay, this is also quite hydrophilic because this uh, you know, proton can be deprotonated. Okay, this one polyamide. Yeah, you can attach the polyamide group on the silica surface. This one, these amide groups are hydrophilic. Yeah, yeah. So this is the hydrophilic surface, and based on hydrophilic interaction, yeah, the why the polar molecules are separated. Yeah, that is called the hydrophilic interaction chromatography. Right? And let's look at this the figure. So far, we have learned a lot of well, a, a lot of things to be considered for HPLC. Yeah. So many things affecting the HPLC separation ability. So, but the question is, how do we how do we select, yeah, the necessary, for example, the columns, okay, or how do we select the separation mode, okay, and then uh, this is called the decision tree. This can be a guide, yeah, to decide which way to go. Yeah? There are two the trees. One is when the molecular mass is less than 2000, and the other one is when it is uh, more than 2000. Okay, let's take a look at this tree first. Okay, when molecular mass is smaller than 2000, and then here, first thing we have to decide is that whether the solute is soluble in organic solvent or in water. Okay, and if it is soluble in organic solvent, then also we have to decide between these two: soluble in non-polar to weakly polar solvent hexane to CHCl3, yeah, or the soluble in moderately polar to polar solvents. Okay, this one, the CHCl3 is a moderately polar one, and this methanol is polar solvent. Okay, yeah, yep. So yeah, with the knowledge of the solute, whether it is soluble in polar or to weakly polar, or moderate polar to the polar solvents. Okay, and then we decide if it is soluble in non-polar solvent, and then the choice is the bonded reversed phase chromatography. Yeah, that's the answer. Okay, and then bonded phase is maybe octadecyl or C8 phenyl. Okay, this one. Okay, cyanogroups. Yeah. And if the solute is soluble in moderate polar or polar solvents, and then here if they decide whether it is soluble in this one, this chloroform, right? Or whether it is soluble in alcohol, nitrate, or ethyl acetate. This is more polar than this one, okay, chloroform. And then if it is soluble in chloroform, and then adsorption chromatography is the one, yeah, is the choice. And if it is soluble in alcohol or nitrate or ethyl acetate, then bonded normal phase chromatography is the answer. Okay. Yeah. And if the solute is soluble in water, and then now decide whether it is non-ionic or ion paired or ionic. If it is non-ionic or ion paired, is that in that case the proper stationary phase is bonded normal phase or hydrophilic interaction chromatography. Okay, and if it is ionic, right, then ion exchange or ion chromatography is the answer. But what if the molecular mass is greater than 2000, and then again first decide whether the solute is soluble in organic solvents or in soluble in water. Okay, and decide since molecular weight is quite high, and then molecular size is important. Okay, if it is less than 30 nanometers, and then bonded reversed phase chromatography is the answer. If the molecular size is between 30 and 400 nanometers, and then molecular exclusion chromatography is the choice. And if the solute is soluble in water, and then decide whether it is non-ionic or ion-paired, or it is ionic. Yeah? And if it is non-ionic or ion-paired, then molecular size, depending on the molecular size, yeah, we decide the stationary phase. If molecular size is less than 30 nanometers, the bonded reversed phase or hydrophobic interaction chromatography is the answer. Okay, if molecular size is bigger, yeah, between 30 and 400 nanometers, and the molecular exclusion chromatography is the one. Okay, and if solute is quite ionic, and then ion exchange chromatography is the answer. Okay, yeah, these two tricks are a good guide. Okay, and also we have to consider solvent. Yeah, this is really important. Okay, usually we use the mixture solvent. Okay, pure HPLC grade solvents are required. Yeah, this is important. HPLC grade. Yeah, this is highest grade, I think, and very expensive. To prevent column degradation and to minimize detector background signals. Okay, so when you buy the solvent, you have to buy HPLC grade solvents. Okay, probably from where Sigma Aldrich or Merck. Yeah. And dissolved oxygen must be excluded by helium sparging. Okay, why? If oxygen enters the column, right, it may oxidize something, yeah, some component in the column, yeah, and that may result in column degradation. Okay, how do we remove the oxygen? Yeah? By sparging, the inert gas like a helium, okay, and then oxygen gas will be, purged out. Okay, a filter is used to make used on the intake tubing in the solvent reservoir to exclude, uh, the particles whose size is greater than zero point 0.5, must be micrometers. Okay, let me check. Wait just a second. Yeah, right. This is not millimeters, micrometers. I didn't convert this m to the Greek. Okay. Yeah. So filter must be filter is used. Okay, to exclude, the larger particles. Sample and solvent are passed through a short expandable guard column. Yeah, we already learned that. Yeah, guard column is necessary to protect the main column. The guard column that has the same stationary phase as the analytical column and retains strongly adsorbed species. Okay, and for the reversed phase separation, at the end, the column should be washed with 10 to 20 mobile phase volumes, okay, of strong eluent to remove strongly retained solute. Yeah, yeah. At the end of the experiment, column must be washed, yeah, with the mobile phase, okay, of strong influent eluent, okay, to remove the strongly retained solute. For the normal phase separation, which is sensitive to water in the solvent, to speed the equilibration of stationary phase with changing eluent, organic solvents for normal phase chromatography should be 50% saturated water. Okay, yeah, that's the idea. And the gradient illusion in reversed phase separations, 10 to 20 volumes of initial solvent should be passed through the column after the run to equilibrate the stationary phase with the solvent for the next run. Okay, yeah. So maintenance of the column is very important. Okay? Reducing waste solvent without sacrificing resolution. Okay, actually, usually, the solvent, okay, after passing through the column, yeah, and to the detector, that solvent is usually discarded. Okay, so it is important to reduce waste solvent. Okay, without sacrificing resolution. Um, how do you do that? Reduce In order to reduce the waste solvent, use shorter columns with smaller diameter particles. Yeah? A shorter column, that means the volume inside the column will be less. Okay, switch from 4.6 millimeter diameter column to 2.1 millimeters. Okay, by decreasing the column diameter, and then we need only small amount of solvent. Okay, for isocratic separations, use an electronic recycler that recycles eluate when no peak is being eluted. Okay, and especially in isocratic separation, right? Where if the detector shows no signal, right? That means what? Nothing in the solution, in the solvent, and then that solvent have to collect and then can be reused, right? Okay, and also it is important to maintain a symmetric band shape. Okay, in a previous chapter we learned, some in many times the chromatographic peak has this kind of peak shape. Okay, this is not symmetric. Okay, this is asymmetric. okay, and this is not a good separation. So making this peak as symmetric as possible. Yeah, that is important. And so how do you know how do you know how asymmetric it is? Yeah? There is a criterion. Yeah? And take the peak height, and then from 1/10 from the bottom, and then you draw this horizontal line, and then you draw the vertical line from the this peak position, and you measure the distance, yeah, the A and B, and then take the ratio A over B. Okay, for the ideal case, the ratio of A and B is 1. Okay, because that is symmetric. But this is an asymmetric, and this A over B may vary between 0.9 and 1.5. Okay, this is called the tailing. Tailing of amines might be eliminated by adding 30 millimolar 3-ethylamine to the mobile phase. Okay, if this is due to the amine, and then uh, one of the idea to eliminate this tailing is to add this concentration of 3-ethylamine, okay, to the mobile phase. Okay, the additive binds to the sites on silica that would otherwise strongly bind on a light. Okay, by adding this triethylamine, okay, and then this triethylamine, the concentration quite high, and then it occupies the site on the silica, right? So that the amines of our interest, cannot absorb on the silica surface, and then that's the way of removing this tailing. Okay, tailing of acidic compound uh, might be eliminated by adding 30 millimolar ammonium acetate. Okay, further, acidic compound, yeah, add this 30 millimolar ammonium acetate. This is ionic, the compound. Okay, for unknown mixture, and 30 millimolar 3-ethyl ammonium acetate is useful. Okay, so if you don't know the the components, yeah, but you observe this kind of tailing, and then you add 30 millimolar 3-ethyl ammonium from here. Let me see, and acetate. Okay, from here. That's the idea. Double the peaks or altered retention time when this is observed, and then change the solvent. Okay, this one, oh, this is quite bad actually. Peak distortion by overloading. Yeah, if you uh, inject too much sample, and peak distortion may occur. In this case, it reduces the sample mass. Peak broadening by excess dead volume. Yeah? And yeah, dead volume is too much, and then peak will be broadened. In that case, use short, narrow tubing. Okay. What is dead volume? Yeah, dead volume is the volume of a chromatography system outside of the column from the point of injection to the point of detection. Okay, yeah, the solvent now pass through not only the main column, but other parts. Okay, then those parts are called dead volume. Okay, yeah, and let me see this one. This sample dissolved in the alcohol, right? And then you see this very bad, yeah, uh, bad chromatogram. Okay, and it said this is double the peaks. Okay, and in this case use different solvent. Yeah, solvent with 9 mixture solvent of water and nitrogen, whose ratio is 9 to 1. Okay, and then you get this very nice looking separation peak. Okay, let's stop here.